right. Okay, lots of examples today because we're going to talk about 2 rules and 1 process. All right. So before we talk about a derivative for a logarithmic function, we must remember our logarithmic properties. If we are multiplying inside of our logarithm, how could we expand that? What do you say? Okay, good. We can add 2 different logarithms together. Bases stay the same. We separate into 2 logarithms that are being added. Okay, good. What if we divide inside of our logarithm? We can separate with using subtraction. And then our last one. If we have something with a power inside, what can we do with that power? Maybe we can bring it to the front. We multiply it out in front. Okay. So what I'd like you to do is I'm going to give you about 1.5 minutes. And I would like you to expand these 2 logarithms with, you guys can work together in your pod, okay? So as a pod, come up with the expansion for these 2 logarithms. Should be working on the second one by now. You're not done already.
Now that's
I'm still not sure I'm comfortable with the part.
Did you see on the comment? Did you see the picture of? Okay, someone took the farm picture and they took
Nope.
Oh really?
Okay, Larry, expand the first one for me.
Okay. Log. Oh wait, no. Hold on. 1/2 log base 5 x plus 1
Make sure x plus 1 is in parentheses. Okay.
minus log base 5x.
Do you agree with Larry? I agree with Larry.
Do the next one.
Sure.
Okay. So it's 3, right?
Mm-hmm.
Natural log x plus 3. Parentheses. Make sure the parentheses plus x plus natural log of x plus 1
Good.
minus 1/3 not natural log parentheses x plus.
Do you agree with Cole? Yes.
Don't you want to put parentheses around the first two because you're dividing the
Um,
entire thing?
That is a good question. Since addition and subtraction are like tied in orders of operations as well as multiplication and division, we read from left to right. So we would automatically multiply these first and then divide, okay? So it would not be necessary, but it is not a bad thing to have them, okay? If we had two items in our denominator, those would definitely need to be in parentheses. Okay, but it is okay in this case not to have. Okay. All right, so we will need to use that throughout the day. Don't forget how to expand. Let's talk about derivative rules. The derivative of the natural log of x. Are you ready? Are you ready? The derivative of the natural log of x is 1 over x. That's it. Yes. This goes into your memorize category. Okay. All right. So not always are we going to have the natural log of just x, right? It is possible to have something inside of our natural log. Do you agree? Okay. So if we have something inside of our natural log, how is that going to look different? What are we going to have to use? The chain rule. So if the derivative of the natural log is 1 over x, the derivative of the natural log of f of x is 1 over f of x, then times the derivative of what's inside. So I'm going to follow that same pattern, but then use the chain rule. Ladies and gentlemen.
Homework.
Let's apply it. Are you ready? Natural log of 2x. Okay? Natural log, the derivative is just 1 over x. So since 2x is inside, the derivative is 1 over 2x. Do we need to apply the chain rule?
No.
Yes. If it's not x inside, you have to apply the chain rule. 2x is inside. What's the derivative of 2x? 2. What's our derivative? Oh, wow. Kind of exciting, right? Next one, natural log of x squared plus 1. Okay. So dy dx. Abram, help me out. How do we do it?
It's 1 over f of x.
Okay, so 1 over x squared plus 1. Multiplied by the derivative of 2x. 1 over f of x times the derivative of f of x. So we have 2x over x squared plus 1. Very nice. Okay, so now let's take it a step further and apply it with other rules. What do you mean by that, Mrs. Coleman? What did you say there, Cole? Is this a product rule? Can you answer Cole's question? Yes. Yes, this is a product rule. Okay? So the derivative of x. Larry, do you have a question?
No.
Okay. Because it's x times natural log of x, right? We have a product rule. So the derivative of x times natural log plus x times, what's the derivative of natural log? 1 over x. So our derivative is natural log of x plus 1. Okay. Another combination of rules. Which rule do we need to apply to this derivative? The chain rule. What is the outside function that f of x cubed, right? We have something cubed. That's our outside function. So to find this derivative, we need to apply the power rule first, and then we multiply by what? Okay, and what's the derivative of the inside?
1 over x.
1 over x. Okay. If you left it as this, I would not count off. All right, I just wrote it as one big fraction. Whichever way you write it, it's not going to be a big deal. All right, so why did I make you do all of that expanding? We haven't even seen that yet, have we? Okay. Write this example down. Do not panic. Trust me, please. Trust me. Right now, does that look awful? Okay? We have a function inside of the natural log where we have a quotient inside of a cubed root, right? What could we use to simplify this a little bit? We can do this without the quotient rule. Okay, so first we could say this is 1/3 natural log of this. I agree. Oh, now we could write 1/3 natural log of x minus 1 minus 1/3 natural log of x plus 1. That's the expanded version of that function. Do you agree? Now, does the derivative look as intimidating? Oh, no. dy dx equals, remember, a constant multiplied to a function goes along for the right. What is the derivative of the natural log of x minus 1? Okay. Minus, when we take this derivative, we have a constant times the natural log. The constant goes along for the right. Okay. Joe, what's the derivative of the natural log of x plus 1? 1 over x plus 1. Now, if we wanted to make one fraction, this would not be a terrible problem to do that. I won't make you. I will let you leave it like this, okay? Keep in mind the book will not leave it like this. They will force common denominators and actually do that subtraction, but it is fine if you leave it like this, okay? Is that much better than having to do the quotient rule? Right? Thank you.
When you said like the one that has to stay on to the right, are you just doing like the product rule and just like simplifying?
Well, I mean, if you do the product rule, the derivative of 1/3 is 0, so that part goes away. You see what I'm saying? It's not necessary to use. Do you remember the constant rule that I told you about? if you have a constant times your function, you can take the derivative of your function and then multiply it by k. Okay. You can do the product rule, you're going to get the same thing, and it is more work than I think is necessary. Now, we talked about natural log derivatives. What about logs that do not have base e? Do you remember how to punch logarithms into your calculator using the change of base formula? Okay. If we had, I'm a step ahead of myself. Okay, in some of your problems, we're not going to do these. In some of your problems, you may see absolute values. Why would a logarithm maybe have an absolute value inside? We can't have negative numbers inside of our logarithms. You're not going to take your derivative any different, okay? The derivative of the natural log of cosine of x, just ignore those absolute values. We have them because we cannot plug negative numbers into our natural log, okay? All right, so our change of base formula, we took the log of x, this number, divided by the log of a, right? And it doesn't matter if you log, natural log, whatever base it is, this was the change of base formula, okay? We are going to use the change of base formula to figure out what our derivative is for a log of base a. Are you ready? So, we're going to take the derivative of log base a of x using that change of base formula. A is a constant, right? Log of base 5, log base 10, log base 15. So the natural log of a, what is that? If a is a constant, the natural log of a is also going to be a constant, right? Are you with me? If a is a number, the natural log of a is something we can type in our calculator. It is a constant. So when we take the quotient rule, low d high minus high, the derivative of a constant is 0. All over the natural log of a squared. Well, we're subtracting 0, so I'm going to go ahead and this is just 1 over x natural log of a divided by the natural log of a squared. Well, one of those is going to cancel out here. And we're left with 1 over x natural log of a. There's your rule. If you do not have log base a, if you do not have log base e, this is your derivative for your logarithm. Does it look very similar to the natural log? You still have the 1 over x. The only thing that is different is you have the natural log of the base underneath. And, of course, if there is a function inside, ignore that. If there's a function in, well, that's not really how I want to write it. Okay. Ignore that, please. If there's a function inside, then we're going to have to use a chain rule. Okay? Sorry, I forgot I had that all typed out when I wrote it. Okay? So we're going to practice a couple. We'll start easy peasy. Log base 3 of x. log base 3 of x. If we take the derivative, what are we going to get, Tammy?
Of like everything, you're gonna get 1 over x natural log.
Good. 1 over x natural log of 3. We still have the 1 over x, but since it's log base 3, we have to multiply that denominator by natural log of the base, which is 3. Okay. Log base 3 of 3x. Okay. When we take this derivative, what is going to be different? We have to use a chain rule. So our inside is 3x. So we have to say 1 over 3x times the natural log of the base. And since we have 3x inside of our logarithm, we have to multiply by its derivative.
So how about 3x squared, we have to multiply it by.
Now, yeah,
So why do you have to use the chain rule for that part?
because we don't have just x inside, we have 3x.
So it's not like, it's not like a compound, or you use the chain rule.
Because 3x is inside of our function. So we take the derivative, keeping 3x inside, and then multiply by the derivative of 3x. Yes?
What's the first one, chain rule 2? You just
If you want to think of it like that, yeah. Did you guys hear his question?
Yes.
You could think of this one as a chain rule where the derivative is 1, and so you don't have to write it. Okay. Let's do this one. What's the base on this one? 10. If there's not a base, we assume it's 10. If you want to write it in so you remember, that's not a problem. Okay. So when we take the derivative, we're going to take 1 over f of x. Just like we do for natural log, but we have to multiply this by what? What'd you say? Natural log of 10, because that's our base, times 2x for our chain rule. So really we have dy dx is 2x over x squared plus 1 natural log of 10. If you don't practice these rules, you're not going to remember them. You have to do your homework tonight. Okay? Now, what is nice about logarithms is they can help us even if we don't have a logarithm in our function originally. What do you mean by that? Write this problem down, please. Okay, we had to take this derivative. We would have to use a quotient rule, and with both the numerator and denominator, we would have to use chain rules. Do you agree? Okay, seems a little bit intimidating. Okay, it's going to be pretty messy. Okay, logarithms give us an opportunity to take a complicated derivative and break it apart. Okay, is there a logarithm in this function right now? No. But what we can do is mathematically it is okay to do something to an equation as long as we balance it out. If we do it to one side, we can do it to the other. So what we can do is we can write this as the natural log of y equals the natural log of x minus 2 squared over square root of x squared plus 1. Why would we do that? Okay, we can solve it easier by doing what to the right side? Expanding, right? We have this big, yucky fraction that we can expand. We could write this as 2 natural log of x minus 2 minus 1/2 natural log of x squared plus 1. Now we have an implicit function where all we have to do is take a derivative of 3 natural logarithmic functions. That's kind of nice, right? Better than the quotient rule with 2 chain rules inside, right? Okay, so the derivative of the natural log of y.
2 times.
Okay, Josh, what's the derivative of natural log of y? 1 over y. And anytime we take the derivative of y, times dy dx, good, equals, Josie, the derivative of 2 natural log of x minus 2.
Would be 1 over x minus 2 times 2.
So you have the 2 times the 1 over x minus 2. Is that what you said?
Yeah.
Yep, and we can rewrite it in a little bit. Minus 1/2 natural log of x squared plus 1. Alex, what's that derivative?
Or 1 over x squared plus 1 times 2.
Because you did the chain rule, right? 1 over x squared plus 1 times the chain rule. Okay, so I'm going to make this right side look prettier. 2 over x minus 2 minus these 2's cancel out and we have x over x squared plus 1. Now, over here, we're finding the derivative, right? So what do we need to do with the left side of the equation? Do we want 1 over y times dy dx? No, we just want dy dx, correct? So how do we move 1 over y to the other side? Okay, so we're going to multiply both sides by what?
Would you be okay if we divided by 1 over 1? And just left it like that?
No.
Really?
First of all, I'm not okay with you leaving y. Why? What kind of equation did we start out with? Implicit or explicit? It's explicit. We made it implicit to make our derivative easier. So I expect that your derivative is also going to be explicit. Okay? So you have 2 over x minus 2, x over x squared plus 1. And then instead of y, you know what y is. Y is x minus 2 squared over square root of x squared plus 1. And since I'm not making you simplify your answers, you can leave it like that. Okay? This is equivalent to what you would get if we would have done the chain rule with the, the quotient rule with the chain rule. Okay? But, in my opinion, this was much smoother. This was a lot less complicated. on logarithmic differentiation. When I ask you to do logarithmic differentiation, I'm going to give you an equation that's not logarithmic, and you're going to make both sides logarithmic, so you can do this. So your homework tonight, which is on your gold sheet, it is going to come from 2 different pages. On page 325, that's where you're going to practice the natural log derivatives. Page 362, those are logs of other base. Okay? Make sure you practice both, otherwise you're not going to remember them. Okay? There are 2 minutes left in class. If your book's not out, you may not have time to get it out and start one, but
The last